Hello Math 1100 students. Lesson 12 corresponds to sections 6.3 and 6.4 of our textbook by Sullivan. Here we are studying transcendental functions. So far we have been studying only algebraic functions, the kind of functions that can be written as a repetition of addition, subtraction, multiplication, division, and radical operations. Not anymore. We're going to learn two transcendental functions, which are inverse of each other, exponential and logarithmic functions. In trigonometry, we're going to learn a whole lot more, but here in college algebra, just two transcendental functions. Okay, here we go, exponent functions, but let's begin with something we already know, and that is the exponent rules. Here's the first line. I hope everybody remember everything here. All good? 0 power is 1, first power is itself, negative first power is reciprocal, and 120 power is 1. How about the second line? I hope everybody remembers. Same base A. In this case, multiplication becomes adding up the power, division is subtracting the power, and power of power is multiplying the powers. The third, well, previously we had same bases. Now we have same exponents, same powers. When we have two or more different bases, the same power is going to be distributed in. Okay, so much for the review on exponent rules. And let us finally define exponential functions. Here we go. A function defined by a to the x power, where a is strictly positive. This kind of function is called exponential functions. Wait a minute. Aren't these just repeated multiplications? In that case, they are algebraic. Well, in fact, when x is a rational number, then this is just algebraic. When x is a whole number, 0, 1, 2, 3, and so on, then we have just repeated multiplication. That's it. For example, if you have a to the 0 power, that means 1 times no multiplication of a, so that part just drops, and then we have just 1. And we have 1 power, then we have 1 multiplication of a, so we have just a. And x is 2, then here we have a times a, kind of like that. And what if we have negative integer, or x is capital X, which is positive, 1, 2, 3, 4. In that case, you can write a to the x power as a to the negative x power, negative capital X power, and then that goes to denominator. And down here, you can have just repeated multiplication. Or you can consider this as overall repeated division. Either way, it works out. Algebraic. What if we have rational power? In that case, it's a radical operation. And it also comes from basically a repetition of multiplication with a bit of conversion as well, this reverse as well. So y is a to the x power, or a to the m over n power, or nth radical of a to the m power. That means y to the nth power is equal to a to the m power, where a and y are both positive. Special case when a is 0, in that case y is equal to 0, but then again in the m should not be negative, so denominator is not 0. Oh, there's all kind of messy exceptions when we have 0 there. So let's consider positives only. Now, everything is algebraic. They're all coming from basically repeated multiplications. And if you recall, multiplication was repeated addition, basically. And here's a visualization. This program is randomized, so you can run it again, and you're going to get different base. Still different base, still different base, still different base. Okay, let's stick to one. Okay, we have this base. A is 1.369 something, okay. And then repeated multiplication of a given by this radical operation for x value n over 20, where the numerator is running from negative 100 to positive 100, which means the overall fraction is between negative 5 and positive 5, and there are 200 dots here. and the increment is 1/20th. Now, what you see here, we have 200 dots condensed in this small picture, so they kind of form a curve. Indeed, if you join them, you're going to get a smooth curve. And that's basically what this transcendental function a to the x is all about. Remember, x is a real number, so there's no disconnection here. If you have just rational numbers, then you have plenty of holes here and there because there are plenty of irrational numbers out there. But then again, those dots are not really haphazard. They're forming nicely like this, so if you join them, you're going to get a graph of a function, graph of a real function, and that is a transcendental function. You see, you cannot get that, nice joining by repeated multiplication or division or things like those. You have to rely upon something else, and that something else in this case was graphical method. Okay, here we just join all those. And then we have blue, red, and green graphs, which corresponds to y equals to 2/3 to the x power, 2 to the x power, and 3 to the x power, respectively. Let's go back to previous case here. This one is not really a graph of a transcendental function, graph of exponential function. Just 200 dots where we have selected rational powers. And if you join them, you're going to get something really similar to that. You can clearly see that, I hope. And there's an association from algebraic to transcendental. It's a big step. And there are many ways to take this big step, but the preferred way that I do is to rely upon graphs. And that's why I showed you those dots and then these smooth graphs. See the connection? I hope everybody saw the connection. Once you do, now let's stick to these graphs. Do you see some properties here immediately? Well, they're all strictly increasing from 0 to positive infinity, apparently. To the left, they're all going down to 0, so horizontal asymptote forming y equal to 0. To the right, they're all going to positive infinity. They're all going through 0, 1, y-intercept, because a to the 0 power is 1. That's easy. And then let's look at the right-hand side a little bit more closely here. 2/3 to the x power blue, and then 2 to the x power red, and 3 to the x power green. They're getting bigger and bigger and bigger as I stay in the same x coordinate value. That's because the denominator, the base is increasing from 2/3 to 3, like that. Blue, red, green. Green is the biggest base. So repeated multiplication of 3 is bigger than repeated multiplication of 2, and which in turn is bigger than repeated multiplication of 1.5. So green is growing the quickest, red is medium, and blue is growing the slowest among these three. Now, what if a is less than 1? Previously, we had 3/2, 2, 3. Now we have 2/3, 1/2, and 1/3. They're all less than 1. Positive, yes, greater than 0, but less than 1. And we have these graphs. 2/3 to the x power, 1/2 to the x power, 1/3 to the x power, blue, red, and green. What are the properties? They're all strictly decreasing. They're going down. To the left, positive infinity, but going down to 0. And then horizontal asymptote forming only to the right. Y equal to 0, only to the right. And they're all going through this y-intercept of 1. A to the 0 power is always 1, so that's natural. Now, look at the right-hand side. As I go to the right, they're all decaying, dropping down, but green is decreasing more quickly, and then red, and blue is decreasing relatively slowest. See? Green is the smallest, and then red, and blue is relatively bigger when we have the same x coordinate values. That means green is decaying, going down more quickly to 0, and then red, and followed by blue. So basically repeated multiplication of 1/3, which means repeated division by 3. So keep dividing by 3 versus keep dividing by 2, which is going down more quickly. And keep dividing by 1.5. You see, that's how things are related. Further relations between those two, and here we have those two graphs put together. As a matter of fact, 6 graphs in 2 categories. Do you see an apparent symmetry? Looks like here, if we take a reflection by the y-axis, you're going to get these, and vice versa. Is that really true? The answer is yes. The right-hand side here can be rewritten as 2/3 is reciprocal 3/2 to the negative x power. 1/2, take the reciprocal, and 2 to the negative x power. Here, 3 to the negative x power. So by taking the reciprocal, you got a base greater than 1. But then again, the trade-off is we have to get negative x power. Now compare the left and right from the second line. Same basis, blue, red, green, same basis, but exponents are from x to negative x. Replaced x by negative x. So what kind of graph transformation is this? It's a reflection by the y-axis, and that's basically what we are looking at right here. Another conclusion you can draw: 95% of the time, maybe I'm exaggerating, 90% of the time we're going to do this when a is greater than 1, because this case can be done by doing all these, complete the problem, and then simply take the reciprocal and flip, and we have this. So it's not really useful to get a new set of formulas for these. It's totally unnecessary. Whenever you have a to the x power where a is less than 1, take the reciprocal and then do this. And then solve the problem, and at the very end take the reciprocal back, and we get this. So it's really pointless to consider any formula method for these. Just do these only. Furthermore, there are some common properties. Domain is negative infinity to positive infinity. We saw those. Yeah, okay, all right. And the range is 0 to positive infinity, never going down to below axis, because you see, no matter how many times you just keep multiplying and divide by a positive number, you're never going to get negative or 0. And finally, y-intercept is always 1. A to the 0 power is always 1. You see it here and also there. That's the summary of all these properties, at least the essential ones. The lone exception is when a is equal to 1. In that case, you get a constant function, constantly 1, and that's an oddball case. We don't usually consider it. And in this case, there's no inverse because a constant function, horizontal line, is not a one-to-one function. Now, one more theoretical stuff, and then we're going to have some example problems in the next video. Please be patient. We will do some problems, but one more theoretical stuff. Among those exponential functions, there's one exponential function that really stands out, the most important one. It's a natural exponential function, where f of x is given by e to the x power, where e is a mysterious irrational number with no end and no repeating pattern, 2.718 or something, called natural exponent or Euler number, named after Swiss mathematician Euler, who lived in the 18th century. And the precise definitions are a little bit difficult, and we're going to do those in calculus. Instead, we're going to resort to a graphical understanding. An exponential function whose slope at the intercept point 0,1 is precisely 1, and that is a natural exponential function e to the x power. Why is this so important? Well, that's something we'll have to study while doing example problems. So let's leave it at that for now, and see you again soon.